Hi class, in this video we are going to cover our lesson from section 3.5 in our textbook. This is a section that brings together what we learned in 3.1 and 3.3 about the relationships between f and f prime, and then what we also learned in 3.4 about the relationship between f double prime and f prime, and then because of that also with f. So I want to kind of start by just summarizing what we realized in those three sections. The first thing we realized was that first of all, the sign of the second derivative, so if it's positive, that tells us, so this double line with the arrow, that means implies, that implies that the first derivative of f is increasing. And the reason for that is because the second derivative of f is the first derivative of the first derivative. So the relationship between f double prime and f prime is the same as that between f prime and f. So we also realize that if f prime, which is the slope of f, and then of course f double prime is the slope of f prime. So if f prime, the slope of f, is increasing, that would mean that f of x is concave up. So that was really what 3.4 was kind of getting at. The sign of f double prime will tell you the concavity of f. The sign of f prime, so related to this, we can know the relationship between f prime and f. So if the first derivative itself is positive, that would imply that f of x, that would tell us that f of x is increasing. That would not be able to tell us about the second derivative though. So cannot be determined from the sign of f prime. So it's the sign of f double prime that tells us the direction of f prime, that tells us the concavity of f. The sign of the first derivative can tell us about the direction of f, but it can't really tell us anything about the second derivative. And then if you look to the other part, so if you're looking at when the second derivative is negative, that will tell us when the first derivative is decreasing, which tells us when the very original function is concave down. So all of those things are connected by the sign of the sign of the second derivative. The sign of the first derivative, so if that were to be negative, that will tell me the direction of f. So that would mean that f of x is decreasing, but I wouldn't be able to determine anything about the second derivative just from the sign of the first derivative, which means I would not be able to determine anything about the concavity of f of x. I need to know the sign of the second derivative to understand the concavity of f of x. Okay, so that's kind of a combination of 3.3 and 3.4 right there. The other things that we learned in like 3.3, for example, we learned that if f prime is changing sign, that means that f of x is changing direction, because the sign of f prime tells us the direction of f. And so if that sign is changing, then that direction on f is changing, which means f has hit a max or a min value. So that was really what lesson 3.3 was about. And f prime changes sign specifically either at a point where it equals 0 or where it's undefined. It's at these places where the first derivative would change signs, which is where f would change directions, which is where it would reach a max or a min value. Similarly, if the second derivative changes sign, so that would be affecting like right here, if it changed from positive to negative, then we can see that f of x would be changing concavity. So two functions ago, before taking the derivative, that's f of x, would be changing concavity. And so that's locating a point of inflection on the graph of f of x. And again, f double prime will change sign where either it is equal to 0 or where it doesn't exist. These are the places where f double prime could change sign. If f double prime changes sign, f of x changes concavity. If f of x changes concavity, that's called a point of inflection, and it's a point of inflection on f of x. It's a 0 on f double prime, a point of inflection on f of x. So that right there is just kind of a summary of what we learned in 3.3 and 3.4. What I want to do in this second part of the first page of this note guide is just kind of visualize, like, what does it look like when you have different signs of each of these derivatives? So for this first box, I have a positive first derivative, which means my function f is increasing. Its slope is positive, and then my function f would be concave up because its second derivative is positive, which means its first derivative is increasing, which means f is concave up. So to be both increasing and concave up would look something like this. And you can see that in this type of curve, your slopes, f prime, they're positive, right? And this is kind of starting off at a small positive, but ending at a big positive. So f prime is also increasing in value. And that's because its derivative, f double prime, was also positive. So we have a function that's increasing and getting a steeper slope as it does that. Now, if our first derivative was positive, so again, we have that our function f is increasing, but its second derivative is negative. That would mean f is concave down. And I wanted to point this out just to show you that a positive first derivative doesn't mean the first derivative is increasing. So positive and increasing are two different things. In fact, this is a positive first derivative, but this first derivative is going to be decreasing since its derivative, f double prime, is less than 0. So f is concave down while going up. So it would look something like this. And so the slopes are flattening out, if you will. So they're still positive slopes, but they're getting less positive, and it forms this concave down type of curve. Okay, and then here again, we have opposite signs between first and second derivative. So the first derivative is negative, which means f is decreasing. The second derivative is positive, which means f is concave up. So it would have to look something like this. The opening of this graph would be like opening up, but the direction of it would be going down. So it's decreasing and concave up. This one, f would be decreasing and at the same time concave down. So it's going to do something like this, it's going to like plummet. Sorry, let me do that again. The slopes are going to just sort of drop off. So they were already negative slopes to begin with, but now they're getting even more negative because they're negative slopes that are also going down in value, which means getting more negative. That's what happens when both first and second derivatives are negative. Now with this one, I wanted to just switch up the language for you to kind of recognize what these are saying. So this is still saying that f is increasing because its first derivative, f prime, is positive, and its first derivative is increasing. This implies that the second derivative is positive, and then that implies that f is concave up. So there's all this connection between. So this graph here is actually the same as this one over here, because to say f prime is increasing is the same thing as saying f double prime is positive. And again, we're just looking at some vocab here. So I have f prime is negative, so f is decreasing. And then f prime is increasing, which implies f double prime is positive, and then that implies f is concave up. So it's going to look like this one, because these words here and here are saying the same thing as f prime being negative and f double prime being positive. So it'd be going down, but concaving up as it does that. And then these last three were just to show the difference between sign, direction, and concavity. The sign of f tells you the sign of f. The sign of f prime tells you the direction of f. The sign of f double prime tells you the concavity of f. So sign, direction, concavity. So for this one, I have a positive sign, so my function is going to be entirely above the x-axis, but it's going to be decreasing the entire time, and it's going to be concaving up the entire time. So it's going to be something like this. like the graph of an exponential or something. So this would have positive y values, negative slope values, and positive concavity. This one is saying that your sine of f is negative. So the graph for this will be entirely below the x-axis. The sine of my first derivative is positive, so that's going to tell me the direction of f, which will be going up. And then the sine of my second derivative is also positive, which tells me the concavity of f, which will also be up. So this function has all negative y values, consistently going up, and then also concaving up. So something like this. Something like that. Like a square root graph or something that was reflected both horizontally and vertically and just goes from here and goes. So it's going up the entire time. It's concaving up the entire time, but these are all negative y values. So again, here I've got the sine of f. So f is positive, so entirely above x-axis. And then that's being contrasted with the sine of f prime, which is negative. That'll tell me the direction of f. It'll be going down the whole time. The sine of f double prime is negative. That tells me the concavity of f. F will be concaving down the whole time. So it'll be kind of like this graph, except it's coming up from above, heading down and concaving down. So something like that. Square root graph going to the left. Or the top half of a left-facing sideways parabola. Anyway, I wanted you to kind of visualize what the signs of each of these things mean as it pertains to the graph of f. Okay, so that's visual. Let's go ahead and just try interpreting the graph of a first derivative. So in example 1 on the second page, what we're given here is the graph of f prime. So I want you to highlight that. Make a note that it's not the graph of f, this is the graph of the derivative of f, the first derivative of f. So these are all the y values along this graph are slopes from the f of x graph. And all these questions that are following that are all asking about f of x. So I can't answer them by just looking at like what this graph is doing. I have to understand that what I'm looking at here is the graph of the derivative of f, and then just go from there. So the first question, part A, is asking me on what intervals is f of x increasing. So I have to think about the relationship between the sine of f prime and how that tells the direction of f. So if I want to know when f of x is increasing, that would be when its derivative, f prime, is positive. So I noticed that on my graph here, here's a section where f prime is positive, here's another section where f prime is positive, and then here's a final section where f prime is positive. Notice that f prime is only changing signs, or possibly changing signs, at the points where it's 0. So maybe I'll make a note of that. F prime of x equals 0 at these three different values, -2, 0, and 2. So those will be potential places where the sign of f prime changes. So it actually doesn't change here, but it does change at -2 and 0. So I notice that on the interval from -3 to -2, my f prime of x values are all above the x-axis, so they're positive. So my function must be increasing there. But also on the x values between 0 and 2, and also from continuing from 2 to 3, I like to stop at 2, and I'll just kind of put a little note about why I did that. It's because f prime of 2 is actually 0. It's not positive. So I can't say it's greater than 0. So I wouldn't say the function's increasing there. So that's kind of why I stopped it there. However, if you said from 0 to 3, I would give full credit for that, because that would be recognizing that the derivative never went negative across this entire span. So I would be okay with that. I do want you to get in the habit, though, of always stopping your intervals at points where the derivative is 0. Okay, so I would put these as my 3 intervals where f of x is increasing. And then I would say because, and here's where I reference the sine of f prime. I would say because f prime is positive, greater than 0 on all of those intervals. So on the AP test, this is a very common sort of AP question. In fact, I stole it from an AP test. When you're asked to explain your reasoning, like it was here, that means that that part is going to be worth a point. And so it means you're going to need to use words. So in this case, and specifically when it's something like this, they're going to want you to talk about the sign of the first derivative. So anyway, something to maybe make a note of. In the second question, it wants us to, again, state intervals where f of x is both. So at the same time, it's increasing, and at the same time, concave up. So increasing is where its first derivative is positive. Concave up is where its second derivative is positive. But for the second derivative to be positive, that would mean f prime is increasing. And so since we're looking at the graph of f prime, I want to look to see where f prime is positive and increasing at the same time. So like slope is positive. Okay, so let's scroll back down. Let me take these off. So the places where this graph is both above the x-axis and also increasing would be here and here. So the y coordinates of each of these points are positive, and the slopes to go from like 0 to 1, that would require positive slopes. Same here, like all these points along this part of the graph are positive, and the slopes, the rate of change to go from this y value of 0 up to here, that'd be a positive slope. So from 0 to 1 and then 2 to 3. So we'll write that down as our answer. So the interval from 0 to 1 and also from 2 to 3. And then when it says explain your reasoning, that's where I would use those words, and I would say because f prime of x, I always want to use whatever function I'm given as my evidence. So because f prime of x is both, maybe I should say that, is both positive and increasing on those intervals. Or you could say like is both positive and has a positive slope, something like that. Wait, and is increasing on those intervals. Okay, so that's part B. Part C then asks us at what values of x, so we're just listing x's, does our function, our original function, have a relative maximum? And then we would have to explain our reasoning there as well. So a relative maximum would happen either at a point where the first derivative changes sign. Well, max would be specifically changes from positive to negative. That's one place where a function will have a relative max. That was our 3-3 lesson. But another place would be at an endpoint if we have them, which we do in this case. We have 2 endpoints. And I know that for 2 different reasons, because I am given this interval in the description with brackets, so that's endpoints. But I can also see on my graph these dots right here, which means the function's not extending forever. It's starting at -3 and stopping at 3. So these points right here are also going to be potential locations or locators of relative maximum. Actually, I'm gonna go back here. So here were the zeros again. These are gonna be where f prime changes sign. At the first 0, it changes from positive to negative. At the second 0, it changes from negative to positive, and then at this third 0, it doesn't change. It's positive to the left and right. So the only time when the first derivative changed specifically from a positive to a negative was right here where x was -2. So that is our first locator for a relative max. So then I need to consider what might be happening at each endpoint. So what I look for again is the sign of the derivative around it. So at the endpoint of -3, my derivative is positive immediately afterward, which means that my function f would start at some place and then it would increase. The first thing it would do would increase from its starting point because of the positive derivative. So that would make this endpoint right here a minimum, a location of a minimum. So not a max, which is what we're looking for here. And then if I check the one over at x equals 3, I notice that the derivative was also positive immediately to the left of that. So again, my f of x function was increasing and then just like stopped. So because of that, it created a maximum value right at the top. So this x equals 3 is locating another relative max on my original function. So we're going to state that here. So first we're going to say at x equals -2, since f prime changes from positive to negative at that point. So that's the first location. And then also at the right endpoint, x equals 3. And we could just say, since f prime is positive, to the left of that point. And that's showing that the function would be increasing all the way until it stopped, making the place where it stopped a relative max. So those two sentences is how we explained our reasoning. And then these were the values of x, where f has a relative max. Okay, then the next question is asking where f of x has a point of inflection. So a point of inflection on a graph is where its concavity is changing. So concavity changes where the second derivative changes sign. And that, of course, is, so the second derivative is the slope of f prime. So we'd be looking to see where the slope of f prime changes sign, and that would be where f prime changes direction. Okay, so if I go to my graph of f prime, again, I'm reading my graph of f prime, and if I look at the directions of it, I notice that it started out by decreasing, change to increasing, change to decreasing, change to increasing. So right here, here, and here, those are places where the derivative, the first derivative graph, changed direction. So that was at x equals -1, x equals +1, and x equals 2. Because the first derivative is changing direction, its slopes are changing signs. These would be negative slopes, positive slopes, negative slopes, positive slopes, which means second derivative is changing sign, which means f is changing concavity, which is a point of inflection. So this function, f of x, has points of inflection at the values of -1, 1, and 2. At the values of -1, 1, and 2. And then for our explanation right here, we would say because f prime of x changes direction at these x values. Okay, so we have learned, or we have seen at least an example of how to read and analyze a graph of a first derivative to tell us where a function is increasing, or where a function might be both increasing and concave up, or where a function might hit a relative max or min, and where a function may have points of inflection. We can tell all of this from looking at the graph of the first derivative. Another thing we can do is attempt to sketch the graph of f. So one thing I would want to say is that we don't know the y values, so these for now are irrelevant. So I don't have any labels on my y-axis because we don't know the starting value of f, the ending value of f, and we don't know how high it goes or how low it goes while it's going up and down. But what we do know, we can tell the direction and the concavity of f if we're given the graph of f prime. So I'm going to use, which is right here. So I can see right here from -3 to 2 and from 0 to 3, my function will be going up. So this is just a first sketch, but I will have a function that goes up and then down from -2 to 0. It doesn't have to go to 0 though, I'm just going down the whole time. And then up all the way until I get to 3. How high it goes or low it goes in the meantime, that's up for debate. But what we do know are these directions. It goes up and then down and then up. Then the other thing I can tell is the concavity. So when the slope of f prime is negative, during that entire time from -3 to -1, my original function will be concaving down. So it kind of goes something like this for that part. So it's increasing and then decreasing, but that whole time it's concaving down. Then I can tell that from -1 to 1, my function is concave up that entire time. So something like this. So it's going down and then going up, but that whole time it's concaving up. This is a point of inflection right here. And then again, I have my graph is concave down because the slope of f prime is negative, which is slope of f prime equals f double prime is negative. That would be a concave down. But notice how f prime itself is still positive there. So my function is still going up, but it's like concaving down. So that would be something like this. And that was up until 2. So it's like concaving down, but going up. And then from 2 to 3, the function is still going up because its derivative is still positive. But now its second derivative is also positive because the slope of f prime is positive. So it's still going up, but it's concaving up. So I can take my other little guide out. That was my direction guide. So I have my direction guide and I have my my concavity guide, and then all together, when you kind of connect it into a fluid function, it kind of looks like this. You know, and again, oh, I should stop it right there. How low or high it ended up, how low or high it went on its intervals of increasing, decreasing, well, that's hard to say. But it would look something like this. And then you can kind of see, like, this would be a point of inflection right here because it was concave up, then it changed concave down. This is another point of inflection. And this is a point of inflection. So point of inflections, they're not max and mins on the graph. They are just places where concavity is changing. You can also see before we said there was a relative max at -2 and then another one at 3. You can kind of see those are standout maxes on your graph. We have minimums at -3 and at 0. So it's just kind of nice to connect it back to our analysis that we did earlier. Lastly, we're going to end with our second example, which is kind of connecting the ideas of position and velocity and acceleration to that of f prime, and f double prime. So we can think of position as f, if you will, although often we refer to that as s of t because that's what our book calls it. And then velocity would be the first derivative of position. So that's the first derivative. We also can call it v of t. And then acceleration is the second derivative of position because it's the rate of change of velocity. So we can think of it as the first derivative of velocity, and then we just also call it acceleration because it is its own function. So we consider position as f, velocity as f prime, acceleration as f double prime. So if acceleration, which is the second derivative of position, if that's positive, that tells me that velocity is increasing, and then that tells me position is concave up. So sign of acceleration tells me concavity of position. Sign of velocity, if velocity is positive, if velocity is positive, that tells me the direction of position. So position would be increasing. So sign of velocity tells direction of position. And then again, if acceleration's negative, then that means velocity is decreasing. And then that means position is concave down. So the sign of acceleration tells me the concavity of position. The sign of velocity, so if velocity were to be negative, that tells me the direction of position. That would mean that position is decreasing. Now, when velocity changes sign, that indicates where our object's position is changing direction or turning around. And again, this is because position is changing direction. I never leave enough space to write all this stuff down. Sorry about that. It always runs over to the side or whatever. Okay. So So that's important, right? Because a lot of times you're going to be asked, when is your object changing direction? And so velocity will change sign specifically at places where it's 0 or undefined. And then that would be where our object is turning around. Now, another major thing I want to clarify too is that when we talk about speed, we're really thinking of it as the absolute value of velocity. So it's like your rate of change, but not worried about direction. Because as we saw here, the sign of velocity, that just tells us direction. But the absolute value, in other words, the magnitude of velocity, that would tell us the speed, just how quickly the object is moving, and it disregards which direction it's moving in. So sometimes you're asked questions, and you'll see like down here, you're asked questions to determine when is an object speeding up versus slowing down. Well, that will have to do with this fact that speed is absolute value of velocity. So basically, it's like the greater the positive or the greater the negative velocity, the absolute value of that will be getting bigger. So situations like this where velocity is moving away from 0, that would be when our absolute value of these velocities is increasing, so speed is increasing. So we also say this, we say that an object speeds up if velocity and acceleration have the same sign. So here, this is an example of that because like these y values of velocity are positive, right? 20, 40, 60. The slope is also positive. It went up 60 over 10, right? So it's a slope of positive 6. So that would be a situation where velocity and acceleration have the same sign, which is causing these velocity values to go up, to increase, which means our speed is increasing from 20 meters per minute to 40 meters per minute to 60 meters per minute. So the speed is increasing. We also say that if, so we say like an object will slow down when velocity and acceleration have opposite signs. So again, it's if these numbers are small positives or small negatives, and then you absolute value them, and basically when these velocity values in here are getting closer to 0, then the absolute value of those is getting closer to 0, which is small, right? So on this graph, it would be this interval here. So you have positive velocity values, but they're heading towards 0 because the slope is negative, right? This has a negative slope. That would be your acceleration is negative. So this would be like positive velocity, negative acceleration. And you can see the velocities are going down from 60 meters per minute to 40 meters per minute to 20 meters per minute to 0. So slowing down. And then another spot would actually be here. Because again, if I absolute value these, it goes from 40 meters per minute to absolute value 20 meters per minute to 0. So anytime the velocity is heading towards 0, we would say that the object is slowing down. And so that happens again when the velocity and acceleration have opposite signs. Here, my velocity values are negative, right? It's like negative 40, negative 20, but the slope is positive. It's going up 40 and to the right 15, so positive slope. So this would be where they have opposite signs, and therefore the object is slowing down. Okay, so knowing all of those things, we now want to try to answer these questions. It's very similar to how we answered the last set of questions, but things are just worded a little bit differently. So this is saying like, over what time intervals is position increasing? When it says object moving right, that's code for position is increasing. Okay, so position will increase when its velocity is positive. So we just have to go to this graph, which by the way is the graph of velocity. Failed to point that out earlier, that's my bad. So we're looking at the derivative graph right now, the derivative of position. So these are actually just this interval right here. From time is 0 to time is 30, all of those times have positive velocities. So my object's position must have been moving right that entire time. So we would just put like from 0 to 30 minutes. And then it's moving left across the other set of time because all these velocities are negative. So from 30 to 55 minutes, the object was moving left. we can see too that it turned around like right here, right where the velocity is 0. It indicates, or not just that, but where it changed from positive to negative. That's how we can tell, oh, that's where our object turned around, because it was moving right, and then it like stops here, and then it turns around and goes back the other way. So that time of 30 minutes was our turning around time. So that would be this answer. This is when velocity changed signs. Now, when the object is furthest to the right, that kind of does involve some chapter 4 knowledge. But for now, I think we could probably just look at this graph. Notice how these velocities are greater. So this object is moving at a greater velocity for a greater length of time. It probably covered more ground during this period when it was moving right than when it turned around and went left, because these are not quite as fast velocities and not quite as long of a time. So I don't think they covered as much distance when they went backward as when they went forward. So I say its furthest to the right was right here when it turned around. So I would say at 30 minutes. And then I would say furthest to the left would be right at the starting point, because, and we don't know where that starting point was, but we know that it went right from there, turned around and went left, but probably didn't get as far going left as it did going right. So the starting point would be when it was furthest left. Okay, so speeding up, here we go. Speeding up would be when velocity and acceleration have same sign. So we're looking for positive y values on velocity, but also positive slopes. So that's here, here, and then we're looking for negative velocities and negative slopes. So that's here. Positive velocity, positive slope, negative velocity, negative slope. That's where velocity and acceleration have the same sign. That would be where our object is speeding up. So from 0 to 10 and from 30 to 40. Slowing down would be from here and here. So positive velocity, negative slope, or negative velocity, positive slope. So that would be 15 to 30 and 40 to 55. Okay. All right. So that's like the typical kind of questions you'll be asked. And then of course, sometimes you're asked to try to sketch. Can you get an idea of the position graph? Maybe we don't know the y values, so I'll just blot those out because they're irrelevant for right now. I don't know how low where the object started. I don't know how high it went. I don't know how low it went. But I do know that from 0 to 30 minutes, it was going up. So like from 0 to 30, my graph was going up the whole time. And then I know that from 30 to 55, the graph was going down the whole time. Go like this. That's what I know in terms of direction. Now I'll add some concavity to that. So I know that from 0 to 10, my position was going up, but also concaving up. So maybe I will go like this. So it's going up and concaving up. Although I don't want it to be that steep, because I'll show you why. Because then at 10, from 10 to 15, it has to maintain that same slope because it's linear right here. So however steep it is at 10, it's got to maintain that same steepness, and I can only go up so high on this grid. So I'll do concave up like this, and then from 10 to 15, it maintains that same slope. And then from 15 to 30, it's going up the whole time, but concaving down. So it's like going like this. So it was like concave up. Maybe I'll do a different color for linear, and then concave down. But it was still going up that whole time. Just concave up, straight, concave down. And then from 30 to 40, it's concave down and decreasing. So something like that. Okay, why is this so hard to draw concavity? All right, concave down. And then from 40 to 55, the position's still decreasing because velocity is still below 0, but the slope of velocity, which is acceleration, is positive. So position would be concaving up even though the function's still going down. So something like We had our points of inflection were right here and kind of there, I guess. Yeah, there we are. So this is kind of an approximate sketch of what, maybe I'll just connect it all, of what my position graph looked like, what my object was doing during this period of 55 minutes. So that will conclude the video lesson portion of today, but there's also a handout that I left with the sub that I want you to work on right now in your groups at your tables together, because I want you to try a couple of these on your own. So I did a couple in the video, but there's a couple more I want you to do. I have an answer key for them posted online, but I want you to do them first before checking. And I hope that it like helps solidify this a little bit. And then of course, there's also the book work for 3-5 that I want you to practice over this weekend. And then that'll be due Monday. And I will be back then and I'll see you then. Thanks. Bye.